I'm Aroni Baduri, and my fellow Team 68 members, Nihar Mehta, Jason Scott, and Andrew Laban, and I would like to welcome you to our macro prototype presentation. In preparation for the colonization of Mars, several tech companies are researching ways to create a living space suitable for an extended visit on the Red Planet. To accommodate for long-term missions, a transportation system that can provide frequent resupplies of materials and goods to astronauts is necessary according to MITIR, or Martian Integrated Terrestrial Environment for Exploration and Research. We were specifically tasked by L3Harris Technologies, an American tech company, to create a small prototype for this future Mars rover, which we call the Mars Cargo Mobility System. We were told that whatever prototype we construct must fulfill general requirements. These included being able to receive and interpret information to follow specific instructions, deposit some sort of cargo, and function completely autonomously. We will get into more detailed specifications later in our presentation. We outlined these general needs and created corresponding objectives. Across all of our goals, we wanted to ensure our prototype could accommodate for any challenge it faced. Additionally, some underlying goals include implementing the most practical solutions that would be least time-consuming, yet most favorable to the prototype's optimization. To keep the design of this project organized, the team decided to designate roles for particular aspects of the project. Nihar and Jason were responsible for the documentation and implementation of Python code when programming the prototype. The functions for the prototype that the software manager had to be able to accomplish included moving in straight lines, turning, varying the speeds, executing actions involved with deployment, and detecting various obstacles. Jason and Nihar were also responsible for the construction of major components of the prototype, which were the base and wheels. They were also responsible for the placement of the Raspberry Pi, sensors, and cargo. I was responsible for the documentation of the process of manufacturing, any setbacks, any breakthroughs, and any experimentation and results. Andrew was responsible for suggesting ideas to the team. Suggestions included features that solved issues for the robot, questioning ideas to ensure that the most efficient design was being implemented, and reinforcing the key purposes and functions that the prototype had to perform. Before getting started on laying out the tasks for the next 8 weeks, our team had to figure out and address the subsystems required for a functioning macro prototype. The prototype needed to have 2 moving parts, one for driving and one for depositing the cargo. Additionally, it needed 3 detection systems for finding lines, magnetic fields, and large-scale objects to avoid. All of these mechanisms will connect back to the CPU, which feeds them power and information. All of these subcomponents will also be protected by structural housing. In order to build a prototype that met the desired needs, there were 5 key actions that had to be done. Number 1 was to set up the Raspberry Pi. This included installing the software, connecting the Grove Pi and Brick Pi, and plugging the cords into the respective ports. The second action was to design the robot. This included creating a blueprint for the structure and Python code that would be needed to operate the robot. The third action was to build the robot and write the Python code. The fourth action was to test the robot, which included debugging the Python code and testing the robot's functionality through trial runs. The fifth and final action was to document the entire process throughout the completion of this project. The actions described in the previous slide were completed throughout the given 8-week time period. This Gantt chart shows how we decided to pace ourselves in completing these tasks. Setting up the Raspberry Pi was done from week 2 to 3, designing the robot was done from week 2 to 5, building the robot was done from week 5 to 7, testing the robot was done from week 6 to 8, and documenting the entire process occurred during the entirety of the 8 weeks. To summarize the specific needs and requirements of our prototype, we outlined its 5 main functions. Essentially, the prototype must steadily traverse the given terrain to specific sites as quickly as possible without dropping the cargo or colliding with any hazards. The prototype must also deposit the cargo accurately and consistently. Included in this table, we have our quantitative goals for each of the needs which we deemed both practical and most optimal for the prototype's performance after studying the project's guidelines and researching various cargo transportation systems. Examples of our target values for the prototype are depositing cargo within 4 inches of the desired drop-off location and it being able to withstand at least a 45-degree incline without dropping that cargo.
This is the decision matrix our team created when it came to choosing what features we should include in the prototype. The first category is how fast we can make the robot go. This had a weight of 5 points. Having the motors on the front wheels did outperform having the motors on the back wheels by a slight margin of 10 points. The second category is the accuracy of our navigation system. This had the highest weight of 20 points. Two line sensors proved to be much better than one line sensor, as two line sensors outscored the one line sensor by 100 points. The third category is the accuracy of the cargo deployment. This had the second highest weight of 15 points. Here the arm clamps outperformed the ramp and conveyor belt system by 30 points. The fourth category is tied for the highest point worth of 20 points. This is the consistency at which the prototype could deploy the cargo. Here the ramp and conveyor belt system outperformed the arm clamp by a slight 20 points. The fifth category was the stability of the prototype. This had a weight of 10 points. The large base here scored nearly double the points of the smaller base. The sixth and final category is the weight of the prototype overall. This tied for the lowest weight of 5 points. A smaller base here proved much better here than a large one by 15 points. Getting to our actual prototype, our team mostly chose what had the best score in the design matrix, but also added new elements that we left out, as well as combined multiple ideas. The hardware mechanics of the base include the following: a rectangular reinforced frame. This reduced the bending of the prototype due to the overall weight of the components. This frame was 26.3 centimeters by 20.0 centimeters. The use of 4 wheels and 3 wheels. 4 wheels were often better at climbing and getting over obstacles, but 3 wheels, 2 powered wheels in the front, 1 pivot wheel in the back, was much better for making tight corners. The elevation of the prototype. The prototype had an elevation of 10 centimeters in the front and 9 centimeters in the back, both relative from ground to frame. This was because of our use of larger wheels in the front. The hardware mechanics of the deployment system include 3 parts. The first being the physical conveyor belt system. 2 belts side by side that were positioned on wheel rims. Both belts were driven by the same motor for consistent speeds. The second part is the walls. We had 2 side walls to support the cargo, as well as a back wall to make sure it did not fall into the Pi computer. The ramp acted as a 4th wall when it was positioned upwards. The last part is the ramp. This consisted of a primary ramp that was 30 centimeters long and a secondary ramp that was 5.4 centimeters long. The primary ramp achieved an initial goal we set of 15 degrees relative to the ground. This allowed for the cargo to retain the correct orientation when being unloaded. The secondary ramp was parallel to the ground to help achieve a higher consistency of successful unloading. Both ramps were flexible. Getting to the hardware mechanics of the sensors and motors, the first thing we decided as a team to implement was the use of 2 line finders that were 5 centimeters apart. This gave us a nearly perfect line detection and only struggled on really sharp corners. The Hall sensor was positioned directly in the center of the robot and quite close to the ground. It had the ability to pivot, so if it struck an object, such as a hill, it could bend upwards and out of the way. We attached the ultrasonic sensor directly on the front above the Hall sensor. This was a good place for it to sense if any objects were in the way of travel of the prototype. 1 large NXT motor was placed on each of the front wheels, allowing each wheel to spin at a different speed. This was most useful when it came to being able to turn the robot.
When designing the software that would allow the prototype to successfully navigate the terrain and appropriately deploy cargo, we first had to figure out the main functions and processes that would allow for the completion of these tasks. Based off of information about the track, we decided on 2 main processes to be coded for the prototype. The first of these processes is line finding. This process would implement the Grove Pi line finders and the main motor responsible for driving the prototype in order to allow the prototype to successfully navigate the course. The successful detection of the black lines of the course would keep the prototype from veering off the track. The second of these processes is Hall sensing and cargo deployment. These 2 functions are combined into one process because they are sequential functions, where the successful deployment of cargo relies on successful Hall sensing. This process would implement the Grove Pi Hall sensor, which detects the magnets at specified locations on the track, and the motor for a cargo deployment system, which runs a conveyor belt. Now, looking at the specific code we use to achieve proper line finding on the course, the first step was to initiate the main drive motors to a set speed. After that, the code would reach the 4 main conditionals we had and continuously update these 4 conditionals in intervals of 0.02 seconds until the program is manually stopped by the user. We had to decide on this interval based on a couple of factors, such as our main speed and the distance between the 2 line sensors. And after numerous tests, we came to the conclusion that an interval of 0.02 seconds would be a quick enough interval so that the robot would not miss a line. The 4 conditionals we used were pretty straightforward. The first one checked to see if both line finders detected white, and if they did, the robot should continue straight. The second one checked if both line finders detected black, and if they did, the robot should continue straight but slightly slower to adjust itself. The third one checked if only the right line finder detected black, and if that was the case, the robot should turn right. Finally, the fourth one checked if only the left line finder detected black, and if that was the case, the robot should turn left. By running through these conditionals continuously, the robot would be able to continuously adjust itself along the black line and not veer off the track. We decided that this was the most efficient method to assist the robot in navigating the course, because in the actual code it only required 4 simple while loops, one for each conditional, and the code was simple and ran smoothly. Our final code for the robot merged these two processes together in a way where the line finding was the main code and the Hall sensing code was in the background. The line finding code ran continuously throughout the whole course until there was user interruption, and the Hall sensing code activated when necessary to deploy the cargo.
After completing our prototype and the software behind it, we of course had to test it out on the course that was given to us. Here's a map of that course. First up was the obstacle. This was a roughly 1-inch tall dowel rod that our robot had to climb over. It ended up taking us almost 2 minutes to get over it, which was much longer than we anticipated. After making some speed adjustments though, we were able to get over the rod. Next was attempting to successfully unload the cargo. We were only able to successfully deposit the cone, and when we did, our prototype missed the first unloading zone and deployed it only at the second one. The cone also toppled over and slid, which left our measured distance at 34 inches, missing our target value by 850%. The next task we were prompted to complete was navigating a sharp dotted line while avoiding a cliff which was simulated by a project kit box. After some turn speed adjustments, we nearly completed it. The transition from dotted line to solid line was too sharp for our robot, and we couldn't completely pass this test. Lastly, our robot was expected to successfully climb a roughly 20-degree hill. This was definitely the highlight of our performance, as our robot only took 2 attempts to successfully completely mount and complete the hill. Our prototype overall performed well. The demonstration highlighted some positive and negative factors of the robot. The robot has a solid structure which allowed it to go through the demonstration without wobbling or tipping over at any point. The robot also maintained the cargo very well during the transport because of the numerous features it had protecting it, such as the ramp, walls around it, and the retention arms. One of the biggest positives of the robot was its mobility. The singular wheel in the back allowed the robot to move with ease and precision. Now for some drawbacks of our design. Although the robot could turn well, it had trouble navigating smaller turns equal to or less than 90 degrees. Additionally, due to the ramp's size of 35.4 centimeters, the robot was not extremely accurate when deploying the cargo. This is because the Hall sensor was at the front of the robot, while the ramp would be deploying the cargo at the back, which made timing deployment difficult. One final negative was the functionality of the Hall sensor. The robot was programmed to deploy the cargo after it detected a second magnet. However, the robot would sometimes detect the same magnet twice, and this contributed to a decrease in accuracy of the deployment of the cargo. So a summary of our project: the robot that we constructed overall met the requirements described earlier. The prototype was able to follow a specific path, detect and avoid obstacles, and carry and unload cargo in a somewhat timely manner. But there are a few things that we could improve upon to increase the robot's efficiency. As previously described in the presentation, there was a problem with the logic behind the Hall sensor. The sensor was only supposed to deploy the ramp whenever it detected 2 magnets. However, due to the robot's hesitation when the path would split, it would detect the same magnet multiple times. We would change the logic of the code so that the sensor would not solely rely on the number of magnets that it had approached. This would ensure that the cargo would deploy at the right place and the right time. Additionally, we would try to find a way to shorten the length of the ramp, because this was a key factor in the displacement of the cargo when it was deployed. The ramp was a total of 35.4 centimeters. This made the deployment difficult because it required extremely accurate timing in order for the cargo to be deployed at the correct place. With these changes, we believe the prototype would prove to be fully optimal in a follow-up project. Concluding this presentation, we want to thank L3 Harris Technologies for this opportunity to propose a design for this macro, which we believe will provide groundbreaking advancements to humanity's future exploration of Mars. Lastly, we want to thank you all for watching our presentation.